In the previous video, we talked about how electron configurations fill orbitals around the atom, starting from near the nucleus, moving outward. And at the end of that video, I mentioned something about bonding behavior as being a direct consequence of electron configuration. In this video, we're going to explore exactly what that means. But first, some historical context. Back in the 1800s, early 1800s, chemists and scientists began mixing various ratios of atoms together to understand how elements combine to what is now essentially understanding stoichiometry. By the mid-1800s, it was well established that certain elements, like carbon, could bond with up to 4 different atoms. So here is carbon bonded to hydrogen. Here is carbon bonded to hydrogen and oxygen. Here is carbon bonded to, say, nitrogen and hydrogen. And in each one of these cases, that carbon atom, that central atom, contains 4 bonds. No one really knew why this was the case until about the mid-1930s, when Linus Pauling and a number of other chemists and physicists started using quantum mechanics to describe chemical bonding. And as a result for this groundbreaking work, Linus Pauling won the Nobel Prize in 1954. And so the theory of chemical bonding in context of science is still relatively new. It's still less than 100 years old. To understand chemical bonding, we need to establish a few rules for chemical bonding. Bonding rules. Number 1, forming a bond releases energy. In order to, if you experience a fire, right, a campfire, the heat that's released is a result of new chemical bonds forming. As a corollary to that, breaking chemical bonds requires energy. And so you think about the gasoline in your internal combustion engine for your car. In order for that gasoline to actually spontaneously combust, you need to put in a spark from a spark plug to facilitate that initial onset of energy. Third, bonding is not a one-size-fits-all. Bonding comes in many forms and is described in many forms. So when we talk about bonding, we can talk about ionic bonds. We can talk about metallic bonds. We can talk about covalent bonds. And we can talk about other types of bonding. And so each one of these is defined in its own way, but they're all kind of on the same spectrum of bonding. So how do we predict what type of bonding an atom will form? Well, in the cases of methane, formaldehyde, and cyanide here, hydrogen cyanide, these are typically what we'd consider as covalent bonds, where we're sharing electrons. We'll talk more about that in a little bit. But bonding itself comes down to the idea of valence electrons. And valence electrons are described as the outer shell. electrons. What do I mean by that? That's not necessarily a clear definition until we go back to electron configuration. So let's look at sodium's electron configuration. Sodium electron configuration, look at your periodic table and count with me. 1s2, 2s2, 2p6, 3s1. This is the outer shell. This is the valence number for sodium. Now, if we look at a different atom, like chlorine, we're going to form a ionic bond here. Chlorine's outer shell of valence electrons. If we look at the electron configuration for chlorine first, 1s2, 2s2, 2p6, 3s2, and 3p5. Now, when we talk about the outer shell of electrons, we are going to include all of the 3s and 3p outer shell electrons. So sodium has 1 valence electron. Chlorine has 7 valence electrons. So let's just imagine what that outer shell looks like. And I'm going to use 2 different colors here. I'm going to use green for chlorine, and I'm going to use orange for sodium. So chlorine here, we have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And sodium has 1. Now, if this was a covalent bond, the electron here between this electron and this electron here between the chlorine and the sodium would be bonded and sharing electrons equally between chlorine and sodium. But as we're going to talk about in the near future, what ends up happening in this case is that in some instances of bonding, those valence shell electrons can transfer. And so if we were to bring sodium and chlorine together in a reaction, what will end up happening is that this sodium atom will move over to the chlorine. And so chlorine now has 8 outer shell electrons. And if we get rid of the 3s1 orbital for sodium, then the outer shell electrons for sodium in this form is also 8. But these are from the 2s2 and the 2p6 valence shell, whereas the chlorine ions, the chlorine electrons, are from the 3s2 to 3p6. And you'll notice here in both cases we have 8 electrons on the outer shell for both of these forms. This idea here of having 8 electrons to make something stable comes out of the idea that when you look at the periodic table, when you get to the noble gases, with the exception of helium, they all have 8 electrons on their outer shell. And they are Nobel-like. So chlorine here is more stable, acting like argon. Sodium here is more stable, acting like neon. And so electrons do all the work because electrons want to stabilize the system. And that rule for having 8 outer shell electrons is called the octet rule. In organic chemistry, we're going to invoke the idea of an octet rule over and over and over again because electrons predict how atoms behave and electrons do all the work.